Oh, hello. Let's see. We're going to look at section 4.1. And this is called Methods of Proofs for Sets. Okay, so we're going to take some of the proof methods that we've learned and kind of readjust them to work with sets. Okay, so we've looked at sets earlier this semester. And we can kind of connect things and see how it fits together. We've seen, especially for predicates, for propositions or universes, that truth sets, kind of what makes a proposition true or not, is a set, so they are definitely connected to each other. So the first proof method for sets, we're going to look at proof using a counterexample. All right, so these are good to prove that two expressions are not equivalent. All right, so these expressions with sets, for example, like example 1 right here, we want to prove that the complement of the intersection of two sets A and B is not the same, it's not equivalent to the intersection of the different complements. Right? Counterexamples are great for proving inequalities or that things are not equivalent, because for those you just need one example that shows that it's not true. Right? When you're proving that something is true with the equal sign, you're basically saying that these two expressions are equivalent for any sets, right? But when so we're looking at an expression like for all sets A and B, right? We want this to be true. We want this to be true, but if you're proving that it's not true, so if you're taking the negation of it, you want to say that there exists sets A and B such that this expression right here does not hold true. Okay, so we're sort of in that situation. All right, so let's find a counterexample. Counterexample. Okay, so we're going to look at a universe and two sets A and B. It could be anything. You can create any universe or two sets. And let's look at these. All right, so here's my universe, 0, 1, 2, 3, 4, 5. Here are two sets from that universe. And we're going to find first the left-hand side. Okay, so let's look at figuring out what this set is. So we're going to take the intersection of these two sets and then the complement. And here you go. The intersection of the two sets is 2, 3. And the complement means what's in the universal set besides this 2 and 3. Okay, so 0, 1, 4, 5. Okay, so that's the left-hand side of the expression. All right, now we're going to look at the right-hand side of the expression. So figure out the complements of each first and then their intersection. Okay, so here in red, I found the complement of A. So what's in the universe that's not in A? 1, 4, 5. Complement of B. What's in the universe that's not in B? 0 and 5. And then we figure out the intersection between these, so they both have a 5 in common. All right, so now we can see this counterexample shows that for these particular sets over that universe, these expressions are not the same. Okay, so if I can find one example where they're not the same, then you say, well, these can't be equivalent for any arbitrary sets A and B. So that that proves that these are not equivalent to each other. All right. Okay, second method of proof for sets, we can prove using Venn diagrams. And we've looked at this previously when we started talking about sets. We did some simple ones. In Venn diagrams, you draw a picture that represents each expression on both sides of the equal sign, and you basically show that the pictures are the same, right? The same diagrams, and that shows that the set expressions are equivalent. Venn diagrams work if you don't have too many sets. Like if you have more than 3 sets, then they become really awkward but they're really great for visualizing what's going on. It gives you a more intuitive feel of these set expressions. All right, so again, we want to look at both sides of the expression, and we're going to look at drawing the complement of the intersection of A with B. Okay, so we're going to draw a universe, we're going to draw sets A and B, and then we're going to find the intersection. So here you go. Here's my universe is the rectangle, and then sets A and B, and the intersection is the shaded area. So this picture right here represents the intersection. Sorry about that. I couldn't pause before I sneezed. So this represents the intersection of A and B. But this tells me I need to take the complement. So basically I need to redraw this, but shade everything that's not in the middle. Okay, so let me put the picture up. So here's that picture. Okay, so this picture right here came from that one. So this represents the complement of the intersection of A and B. Okay, so everything shaded except what was original. All right, so this is this side of the equality. That's what this picture, this Venn diagram represents, this expression. Okay, so let's go with this one. So we want to draw this kind of with several pictures step by step and see if the resulting diagram looks the same. All right, so let's start with a complement of A. Okay, so here you go. What I drew there is the complement of A, which means everything in the universe that's shaded outside what's in the A circle. So this is AC. All right, next I'm going to draw the complement of B. Okay, so this other triangle here represents the complement of B. So everything in the universe shaded except in the B circle. All right, and now we need to put them together. Now we need to find the union of these. So the union is, if you look at the two pictures, is everything that's shaded, regardless of whether it's green or orange. We're kind of putting them, imagine we're putting the orange on top of the green, and let's see our resulting set. All right, so here's our resulting set. So we can merge these together. We find the union. Okay, so this represents complement of A, union, complement of B. Okay, now we compare and we see, yep, this is the identical picture. Everything shaded apart from that sliver in the middle. So these must be equivalent sets. All right, okay, let's move on to the next type of proof. So the next proof method for sets is proof using membership tables. This is basically truth tables. So we want to see if these expressions are equivalent, so they must have identical entries in the truth table. Now the truth table for sets, we're going to use ones and zeros, but they still represent true or false. But what we're talking about is like, I'm going to take an arbitrary member of a set. And if I put a 1 in the membership table, it means that I'm saying that element is in set A, or that element is in set B. So a 1 represents that the element, that arbitrary element, is in this particular set. And if it's a 0, then it's not in that particular set. Okay, so we start building the membership table just like an ordinary truth table with A and B and C at the top. So I need 8 columns in this case. So here we go. I drew my 3 columns with the usual setup for 1s and 0s. And now we start doing operations. Okay, so the first operation we need to do is B intersects C. And here it is. There's a column for B intersects C with the appropriate 1s and 0s. So an intersection is a conjunction. It's an and, right? Because that's what the meaning of it in terms of sets. So again, basically, the 1s means that this arbitrary member that I'm thinking of, a 1 says this is is an element of A and it's an element of B. So because it's an element of both of them, this element will also be in the intersection. All right. Looks like I missed one. All right, so let's see if we can fix this. All right, let's fix this. So, oh no, we're doing B and C, so that was correct. Yeah, B and C. So if it's a 1 and a 0, the element is in B but not in C, it's not going to be in an intersection. If it's 0, 0, the element is not in either, then it's not going to be in the intersection either. So that's sort of the meaning of ones and zeros when it has to do with sets. All right, so then we're going to extend the table and come up with a U, B, and C. All right, so we're going to fill this. So now we're looking at the union of A and intersection B and C. So the element could be in either one or the other or both and be in this resulting one. So I have a 1, a 0. Nope, that's a 1. Let's fix that. Okay. 1 and 0 gives me 1, and another 1, and another 1. And this is a 1, but this is a 0. And this is a 0, and this is a 0. Okay, so those are the results. All right, now we're going to look at this second part. So let me choose another color here. There you go. So we're going to start doing this in pieces. So A union B, looking at the first columns, 1, 1, 1, 1, 1, 1, 0, 0. And then we need a union with C. So 1, 1, 1, 1, and 1, 1, 0, 1, 0. Oops. There we go. Okay, and now we're going to put these together with an intersect. So I need this intersected with this. That's the intersection between these two. So we need 2 ones to make a 1. So we get 1, 2, 3, 4, 4 ones, 5 ones, and then 3 zeros. There we go. Okay, and then we compare. Because these are identical columns, that says that these are equivalent sets. They're exactly the same sets. All right, so proof using membership table is basically the same idea as showing that 2 composite propositions are equivalent to each other when we're doing propositional calculus. All right, let's look at the next example. All right, so this takes us to proofs by definitions, and this is the preferred one in math by mathematicians because it's the most versatile. You can do this with like any number of sets. As I said, Venn diagram and membership tables are limited by how many sets you have because once you get past 3, then they're very awkward. So this is looking at the definition of equality of sets. Okay, so we know from before that 2 sets are equal. If we said set A equals to set B, that means every member in A is a member in B and vice versa. They have identical members. But another way we looked at the definition previously is that if they're equal, that means A is a subset of B and B is a subset of A. So if they're subsets of each other, then they have to be equal. Okay, so this is what we're going to use in these proofs by definitions. So there's 2 steps to the proof. You have to show both ways. Okay, so first step 1 is to show that A intersect B complement is a subset of A complement intersects with B complement. So you have to do this first. But you also have to show it the other way around. You have to show that the intersection of the complements is a subset of the complement of the union. If you don't show the second way, then your proof is not complete. Okay, so if you just show step one, you're only showing that this first one is a subset of the other, but you're not showing that they're equal, that they're equivalent. Okay, you'll notice when we do these that step two is going to be pretty much step one all written backwards, but you have to do it in order for the proof to be complete. Okay, so here's the way these are set up. Okay, so we're going to start with X is an arbitrary member of one of the sets, my first set. So you can say X belongs is a member of this set, complement of the union of A and B, and this is given. Right. So because I'm looking like an arbitrary member, and we're basically following it along, and our goal is to show that if I take any member of this original set, it's also going to be a member of the second set. And that way you prove that the first set is a subset. Okay, so you can't use like specific values for the members. You use X as an arbitrary member. All right, so we're going to use some definition to rewrite this. So if X is a member of the complement of AUB, then that means that X is not a member of AUB. And this is just the definition of what a complement is. Okay, now I'm going to say that it's not true that X is in the intersection of AUB. Okay, and this is just the definition of what a negation means. Okay, so basically our goal here is to change sets to propositions, because we know how to work with propositions. So basically I just changed it to not P. So if you kind of think of this as a proposition P, then I changed this to not P. So all the propositional rules or laws now apply, okay, which is kind of neat. All right, so I'm going to say it's not true, okay, and then I'm going to use the definition of union. So X in the union of A union B means that X is in A or X is in B. So this is the definition of what the union of two sets means. Okay. All right. So I'm negating the or of two propositions, so I can use De Morgan's law. So this is not X is in A and not X is in B. So this is De Morgan. All right, now we're going to work backwards a little bit. So we're going to change things back to sets. So not X is in A, that means X is not in A, and X is not in B. So this is the definition of negation. All right. Then we're going to say that if X is not in A, X is going to be in the complement of A. And X not in B means that X is in the complement of B. So this is the definition of a complement. Okay. And notice that basically we're almost there. So that this means that X is in AC and in BC. Okay, which basically means that X is in AC. Actually, I could probably skip. Okay, I don't think that's necessary. Because if you say X is in this set and X is in that set, you can say that X is in the intersection of those two sets. So this is just the definition of intersection. Right, so that takes me, I showed that if I started X in an element in this set through these kind of definitions, you proved that X also has to be in the second set. So we proved that the first set is a subset of the second set. All right, so now we're going to do it the other way. All right, so let me pick step 2. In step 2, we need to show that the second set, complement of A intersect complement of B, is a subset of this. All right, so let's look at the steps. So we start with X being an arbitrary element of the intersection of the complements. So this is given, that's the start. All right, so that means that X is going to be in AC and X is going to be in BC. That's the definition of an intersection. All right, so this means that X is not in A and X is not in B. Okay, so that's the definition of what a complement is. All right. Okay, so we're going to change this to propositions. So X is not in A means that it's not true that X is in A. And X is not in B, not true that X is in B. Definition of negation. All right. And we're going to use De Morgan's law backwards to pull out the negative. And say it's not true that X is in A. This changes to or X is in B. This is De Morgan. Okay. This means that it's not true that X is in the union of A and B, because that's what this means. X is in A or X is in B. So this is definition of what a union means. Okay, we're going to get rid of the negation and say X is not in A union B. That's the definition of what a negation is. And then this means if X is not in this set, that means the X is going to be in its complement, like this. So that's the definition of a complement. All right, so I got to the end. X is a member of my original set. We proved that X has to be a member of the second set. So the first set is a subset of the second set. Okay, so once you show both steps, again, you can see that it's like once you did one step, the second step is going backwards. Then that shows set equality. All right.